Bismillahirrahmanirrahim. Assalamu alaikum and welcome back. You must know that data traffic is bursty in nature. However, it has been noted that data traffic is not only bursty at one time scale, it is bursty at many different time scales. So what this means is that if you observe data traffic for an interval of, let's say, 1 millisecond, you would observe that the data traffic is bursty. You have clusters of activity and clusters of inactivity. If you were to observe the same traffic trace now for a period of 10 milliseconds, so you've compressed the time signal, you would observe that the signal again has burstiness, and in a sense it is similar to what you observed for the earlier time period. And this would happen for many different time scales. This is at odds with what we would expect with traditional traffic modeling approaches. So we have observed that Poisson arrivals can be used to model the arrival of packets in a data network. And this is traditionally how things have been modeled for data networks. However, for Poisson arrivals, it has been observed that if you aggregate the process, in other words, if you change the time scale, the burstiness would, soon enough go away. In other sense, said differently, if you aggregate the time series, you would have a more smooth time series. But this is in conflict with what we actually observe. In a sense, data traffic is a little more rough than what we would expect from simple mathematical abstractions that we have traditionally used to analyze data traffic. So how do we go about analyzing data traffic and its inherent roughness? There is a field of science which was developed in the late 20th century, which is the field of fractals, which actually deals with the same topic, that is the study of roughness. Before 1970s, when this field was opened up by the seminal work of Benoit Mandelbrot, there was not much work on studying the natural shapes that exist in the world. Before that, we had mathematical abstractions which were very coarse approximations of real objects. Real objects were a lot more rough and complex than what we had in typical Euclidean geometry, the one that you must have studied in your high school, the ones in which we have ideal shapes like lines, circles, triangles, cones, and so on. Rarely do we find something that is real found in nature that can be approximated to a close degree by such objects. Such Platonic objects have limited ability to model the complexity and the roughness of real objects. In data networks, again, the simplistic models that we had before were like the Euclidean geometric objects, that they were very coarse-grained approximations. But we need a more accurate representation of data traffic that is able to capture the burstiness of data traffic at different time scales. And so for that, we study the topic of fractals. And we try to see the parallels in the field of fractals, which studies the roughness in geometrical objects and how that can be applied to create fractal processes that represent data traffic. So today's session is going to be about fractals, their defining characteristics, and how they are different from traditional geometrical objects, and how we have a specific kind of statistics that applies to fractal objects. And we would see that they have some very counterintuitive properties. And if we were to naively apply the traditional statistical methods to such objects, we would have answers that are either somewhat off the mark or even very plain wrong and misleading. So let's start by talking first about fractals. Fractals were created by Benoit Mandelbrot, who discovered that the traditional Euclidean geometrical objects are not complex enough to model real-life natural objects. And he said, and he worked on many different areas of this overall field, and he discovered that natural objects are much more complex. So a very oft-repeated quote of Mandelbrot is that, clouds are not spheres, mountains are not cones, and coastlines are not circles. While we do approximate these natural objects by such simplified Euclidean objects, but such an approximation is a very coarse-grained approximation and way off the mark if we were to look at the fine and intricate details of natural objects. So if you observe natural objects, they have a lot of detail, and the amount of detail depends on the scale of measurement. So let's have a look at some fractal objects. So you have an example of a coastline. A coastline is an object which has details no matter how much we zoom in to the object. So if you were to look at a coastline from a satellite, you would have some representation of what the coastline looks like. But if you were to zoom in, you would find new patterns, you would find new bays and new inlets. So you would have many intricate patterns that were hidden at a scale which was a more higher level look at the object. As you keep on zooming on into this object, you find more and more details. So this is a fractal object, and one defining characteristic of a fractal object is that as you keep on zooming in, you would find more and more detail. The object does not become featureless. Another example of a fractal object is a river, and you would see that rivers typically are quite jagged and they do not follow any of the Platonic Euclidean object that you would study in your high school geometry. Other examples would be mountains. Mountains again is sometimes approximated as a cone, but when you look at it more minutely, you would observe that it has a lot of detail. So again, perhaps not very well represented. In fact, it is not very well represented by a simple Euclidean object. You would require such Euclidean objects to act in a very complex manner, in a manner which we would find in fractals, to form the real fractal object. So you would have a lot of detail. We'd be later on seeing that fractals can be created from simple starting objects, and we keep on iterating. So we do repetition again, and again, and we find that from such simple starting point and such simple principles, we actually create very complex objects, and that is again one defining feature of fractals. So if you observe the sky on a rainy day or before the rain, you would see that the sky has clouds. So how would we classify a cloud as a geometrical object? So we cannot call it as a sphere because it is quite jagged. It has many edges, and an interesting property is that if you look at a subpart of the cloud, that is like the whole cloud, and in fact even that subpart has more details. You can think of edible examples like a cauliflower. So if you take a cauliflower, again it has many minute florets, which is like the whole cauliflower. Again, if you keep on looking inside and inside, if you keep on zooming on this cauliflower, you would see that you find more and more details. If you look at the instance of lightning in the sky, you would observe that the lines that we have is not a straight line. You have a very complex structure there. Again, even in nature, if we observe nature, if we observe things like how trees formulate these simple patterns, it looks like Allah Ta'ala has created this universe through some rules which are happening in a simple iterative manner. So the plant grows in a manner in which the small branches are like the big branches, and the big branches in fact turn out and grow into a lot more bigger branches. And you can see examples of fern leaves in which you can create this pattern. In fact, such patterns can be created by computer graphics, in which we apply simple rules and we create very intricate patterns. And that is the beauty of Allah Ta'ala's creation, that He has very simple rules, and you create such intricate patterns through iteration of such rules. So this is a conjecture. This is, it looks like the operation of nature seems to be working according to such fractal rules. Even on our insides, we have fractal shapes. So there has been a lot of debate on what is the volume of a lung. And there is no single estimate that is accurate enough. And that is because the lung has a very intricate structure. It is a very complex object. So you can observe the lung on the screen now, the bottom right figure. You see that it has a very fine structure. And the higher scale structure is like the smaller scale structure. So we can say that the lung has a fractal structure. So we've seen some fractal structures. Now we can talk about what are the properties that make an object fractal. So one property is self-similarity. That is, if you keep on zooming into an object, the smaller part of the object is like the bigger part. So we can see an example on the screen now. You would see some small pieces of a cauliflower. And if you observe all of them, the florets on the upper half of the screen, you would say that they are pretty much the same, but they are in fact different parts of the cauliflower. If we were to put them together, you would find that one part is a lot more larger than the other part, and so on. But if you were to zoom in enough on these small parts, you would say that the smaller part is almost similar to the larger part. Not exactly, but very similar. Not identical, but quite similar. So this is usually how real life fractals happen. We would see that the idealized fractals have infinite amount of details. But in a real fractal, you have limited self-similarity and limited details at finer and finer levels. And this is because of practical concerns. Obviously, you cannot have infinitely fine structures because there would be some physical constraint. For example, if you were to look into a cauliflower, you would keep on zooming. Soon enough, you would reach the realm of the atomic world. And again, if you keep on zooming, you would approach the level of a quark, and beyond that, it does not really mean anything that your structure has details even at that point. In fact, we would see that real life fractal objects have these fractal like characteristics on many orders of scale. So if I say the fractal characteristic is on 2 orders of scale, that would mean a factor of 100. 10 raised to 2 is 100. So if you were to zoom in 100 times, you would observe similar characteristics. So real life objects have such properties over a range of scales. Another property that fractals have is that they have inexhaustible details at lower and lower scales. So to really understand this, first let us consider a shape that is non-fractal. So let us take any example from Euclidean geometry. So we take an example of a circle. So in a circle, if we keep on zooming into some part of the circle, we would see that soon enough the details would be dilated, and in fact you would reach a point in which you would see that the circle is losing most of its detail, and after some time you would find a straight line, which basically tells you that the show is over. There is nothing more beyond this stage. So this is in contrast to fractals, because in fractals, when we zoom in to some part of the object, we would find more and more details. So you have a very rich structure. And if you keep on zooming in, you would keep on finding more and more details. And when we are talking of an idealized fractal, this would keep on going infinitely long. Obviously, this cannot happen for real objects that have fractal-like properties, but in idealized fractals, if we compare it to idealized Euclidean geometrical objects, you would find that the fractals have inexhaustible richness of structure. This is very important, and this is actually the defining feature of fractals in addition to self-similarity. So real objects may actually fall short on both accounts. They might not have exact self-similarity if we keep on zooming in. And in fact, they might also not have inexhaustible richness of structure. Beyond a certain point, real life, fractal-like objects would not have, a lot of detail. So this is, again, I would reiterate that real fractal-like objects display fractal behavior over some range of scales. So if this range of scale is wide enough, for all practical purposes, we would call this object as a fractal. So one consequent of this property is that fractals are basically scale invariant. So this is a kind of a symmetry. So for example, if you think of a sphere, it has rotational symmetry, which means that if you rotate the sphere, it would keep on looking the same. So symmetry, we would call it as remaining the same when subjected to a change. So scale symmetry would mean that if you were to change the scale of the object, you would still have a symmetry. Ideally speaking, you have exact symmetry, identical. The small part is exactly like the bigger part. But for practical objects, this similarity may be statistical. That is, it would look like both of the objects are coming from the same distribution, but they do not have the same structure. Exactly, same structure is not repeated at smaller and smaller scales. One field in which we find this scale invariance, and there are many applications of scale invariance as it applies to fractals. One of the important applications is to geological surveys. So if you see the screen now, you would find two pictures, and this is obviously a picture of the Earth, but we are not quite sure at what scale is this image taken. In fact, you have two images. So is it from 1 feet away, from 10 feet away, from 100 feet away? So we are not quite sure. So typically how, it's a cardinal rule which geologists follow is that they would put an object in the picture itself which gives an idea of the scale of the image. So typically if they're taking a picture, they would put the lens cap into the picture, and knowing the size of the lens cap, you can calibrate and imagine that this is the scale of the image. So we have two pictures, and you have the lens cap shown in both pictures. So you can conclude that basically they have the same scale, except that this is a trick picture. If you see the upper figure, now this is shown in a more honest manner. The upper picture has a trick lens cap which is very huge, and in fact you can see a person standing next to it. And for the bottom figure, you have the finger pointing to the real lens cap that we are more accustomed to. So the point which actually I'm trying to make here is that both of the picture look the same. In other words, they are scale invariant. If it was not for the presence of such anchoring objects through which we can find out the scale of the picture, we may practically think of both the pictures as belonging to the same scale. This is one of the defining characteristics of fractal objects and fractal processes. We will see that fractals belong both to the geometrical world where they define shapes, and they also belong to the time world in which they define processes. In both the worlds, if you zoom in into some part of the fractal object, you would find that despite the scaling, the new object is symmetric to the original object and it looks the same. This is what we mean by self-similarity. One way of creating fractals is doing iteration, using a simple formula or a simple process, and if we keep on doing that again and again, we find that we form very intricate patterns, very complex objects. One example of this is to have parallel mirrors. So if you use two mirrors, you can formulate an image like the one you see on the right side of your screen now. And you find that there is practically an infinity of reflections. Not exactly infinity because of practical constraints, but because of that, it has a beautiful aspect to it. In fact, much of the things we perceive to be beautiful are because of our appreciation of symmetry. Our bodies even are symmetric, mirror symmetric. The left side is like the right hand side on the outside. It's not the same on the inside, but we have mirror symmetry on the outside. And more the left side matches the right side, the more we find a person beautiful. Similarly, an object, if it has symmetry, it looks very beautiful. You have a similar pattern on the left hand side in which you have a box, and inside the box you have the same image repeated ad infinitum. But obviously, because this is a practical image, a practical box, the repetition cannot go to infinity. But this is a very simple process. Using a simple mirror, you can create fractal-like characteristics. In fact, you can use a projector and you can create similar images in which what you are filming is being projected. And if you create such an infinity, you can create very intricate, complex patterns that look very beautiful. Let us have a look at one of these beautiful patterns that can arise from simple application of iteration. So if you see the screen now, you would find a very simple formula in which we are doing repeated iteration. So z is a complex number. You start with a value of z 0. Typically this is 0. And for different starting points, different values of c, what you do is you keep on calculating the right hand side, and that would be the next number of z. So, and then you would replace that into the formula and recalculate. And if you keep on doing this iteration, you would find that some of the numbers would blow up to infinity and the others would remain bounded. So this is like an emblem of fractals. This is again created by Mandelbrot, and so this set has his name as well. So this is the Mandelbrot set, and this structure looks quite beautiful, and that is because it has symmetry. And if we keep on zooming into it, we would find that, you know, this set or this picture has infinite resolution. You would keep on zooming in and you would find more and more patterns. And those patterns are very beautiful to see. And that highlights that simple rules can create very intricate patterns. So we keep on zooming and we keep on finding more and more patterns. So this is the beauty of fractals. So let's now talk in some more detail about self-similarity. Let's see an example of a self-similar object. This is known as a Sierpinski triangle. You start with a triangle that is filled, but you take the middle points and you take out the inverted triangle from the middle of this original triangle. So if you do that, you will create 3 scaled down versions of the original triangle. I hope you understand the rule. Now, if we were to repeat this, this is to make it more clear to you. Let's do this one more time. So now every triangle that you have, you would keep on applying this rule. You take the middle points and remove the middle inverted triangle. And we do this obsessively. That is, we will do this again and again and again. So now let's do it another time and another time. And we would see that now you have a structure which is self-similar, in that every smaller part of this structure is like the bigger structure. And in fact, that smaller structure again has infinite amount of resolution. If you were to zoom in, as you would see on the screen now, we are zooming on to one part of the triangle. You would observe that there are many different Sierpinski triangle inside that small triangle. And this is a fractal for you. This is an ideal fractal having infinite resolution. So this brings us to an important point and something that people often find counterintuitive. Fractal objects do not always have integral number of dimensions. So fractal objects do not have to have a dimension of 1, a dimension of 2, a dimension of 3, and so on. In fact, they can have fractional dimensions. This is again in contradistinction with what we study in our high school geometry. We see that a 1D object is a line, a 2D object is a surface, a 3D object is a solid. But we can have something in between if we study fractal objects. And this is one of the advancements that fractals have made to our understanding of shapes. So the idea here is, if you observe, you would see a one-dimensional line, a two-dimensional square, and a three-dimensional cube. Now we want to have a generalization of the existing concept of dimensions and see how we can extend it to include fractional dimensions that can specify fractal objects as well. So to do that, what we come up with is a principle, and we say that if we multiply by a factor of f in each dimension, we would get f raised to d copies of the original, in which the exponent d is the dimension. So to understand that, let's see at a line. If we were to multiply it by 2 in every dimension, you only have a single dimension. So when we multiply, we have 2 copies of the original line. So the dimension here then is 2 raised to 1 and d is equal to 1. So if we talk of a two-dimensional square, if we double the dimension in every dimension, we would see that we would get 4 objects that are copies of the original. And in that case, the exponent is 2. 2 raised to 2 is 4. And because of that, a square is 2-dimensional. For a 3-dimensional cube, if we double in every dimension, we would see that we get 8 copies of the original, and 2 raised to 3 is 8. So we say that the dimension of a cube is 3. So this works well for the typical Euclidean objects. Let us see how this works for self-similar objects or for fractals. So let's take the example of the Sierpinski triangle. Now if we take one part of it and if we double it in every dimension, so if we increase it by a factor of 2 in every dimension, you would see that it is now looking like the original object. And now it has how many copies? So if you observe that doubling the size has created 3 copies of the original from where we started. So we increase it in every dimension by 2 and we create 3 copies of the original. So using the principle that we've defined, we say that 2 raised to d is equal to 3. And using logarithms, we can now calculate the value of d. This comes out to be 1.59. And this is very interesting. If you observe it, it's between 1 and 2. So it has more dimensions than a line, but it's not quite a surface. And we can observe it when we see the object. The object has multiple holes inside. So it seems to be a fair reflection of what this object really is. Let's take another example. So now the self-similarity that we'd be seeing is exact self-similarity. So in an exact self-similar object, the smaller part is exactly like the original. And in fact, Sierpinski triangle also was exactly self-similar. We would be seeing that in fact many real objects are not exactly self-similar, but they are statistically self-similar. This object, the Cantor's set, was actually proposed by someone known as Georg Cantor, who is also the inventor of the set theory. And he worked on proposing the concept of infinity as we know now. So this is also known as Cantor's dust. And the idea is quite simple. The idea is that you start with a line and then you break it down into thirds. And then you drop the middle third. Simple enough. But we now apply this rule iteratively. For every line that we see, we break it down into thirds and we drop the middle third. And you would create more and more copies. So intuitively you would say that if you are throwing down everything, sooner you would come to a stage where basically you don't have anything. Not the case. You would see that in fact, if we continue this, you would not have the lines approaching to zero. In fact, you would have infinity of lines. And in fact, you would have infinity of infinities. This is quite counterintuitive, but let us see where we get by applying this iterative rule again and again. So we take this line, we break it down into thirds, drop the middle third of the line, and then create two more lines. So if we keep on doing this, so we get more and more details. So beyond a certain point, we will not be able to visually make a distinction. In fact, we have limited number of iterations shown here, but if you were to do it again and again, the thing that you would get at infinity is the Cantor's set. And if you take any line there and you repeat the process, or if you zoom into it, you would find that even that one line at a very small scale actually has infinities of smaller lines coming inside it, or at a lower scale. So this is again counterintuitive, the concept of infinity of infinities. But let's see how this applies to the world of networks. In fact, this application was first discovered again by Mandelbrot, who is literally a polymath who has meddled in many, many different fields. He has worked in economics, he has worked in computer graphics, and many different fields. He has also worked in application of fractal ideas to telecommunications. And this is because he was an employee of IBM. And IBM was facing a practical problem in 1960s. And that was transmission lines were affected by noise. So they got their engineers to start looking at the noise and try to characterize the noise so that they may create counter methods in which we can actually mitigate the effect of the noise. So when Mandelbrot started looking at the noise, he discovered something very interesting, and he discovered a parallel with the Cantor's set. And that was, if you graph the transmission line and the noise on it, you would see that the errors come in clusters. So if you were to plot it over a period of one day, as you can see on the screen now, you would find that noise comes in clusters in which you have periods in which you have no noise. And then you have periods in which you have intense noise. But what he discovered was, if you were to zoom in into one part in which you have noise, into a noise cluster, you would observe that that cluster has further on the same structure as the original time series. In fact, inside a cluster, you have cluster of noise periods, and you have instances in which you don't have any noise. And he discovered that even for smaller scales, for example, if we were to plot it for 1 second, you find a similar structure. Mandelbrot said that the noise pattern was self-similar with a vengeance. So this is how he described it. And this actually has a parallel with what we've just studied about Cantor's set, because if we imagine this to be, if we zoom in further and further on, we would see that it has more and more details. And if you observe the Cantor set that's shown on the screen now, you would see that there is a close parallel. And in fact, the coming of the noise on the transmission line had a fractal structure. So the things that apply to the study of structures like Cantor set also do apply to the study of noise. One thing I'd like to say here is that when originally mathematicians came up with objects like the Cantor's dust or the Cantor set, it was treated with much skepticism, and that was because it was thought of as a monster, something that they could not deal with traditional mathematics. And many prominent mathematicians took opposition to the ideas of Georg Cantor. But the ideas of Mandelbrot have shown that this is not an isolated incident. This is not a case that is just one-off. But in fact, this seems to be more of a norm, that in many different diverse scenarios, you find fractal properties, properties of self-similarity, properties of richness of structure. Okay, so let's now proceed and talk of another exactly self-similar structure. And this is the von Koch snowflake, also called the Koch curve. And in this, we again start with a line, but now actually create the two edges of an equilateral triangle on the middle part of the line. So if we were to divide the line into thirds again, we drop the middle third and we create two sides of an equilateral triangle on top of it. And we keep on doing this. So that is the method of creating fractals, iteration. So we observe more lines and we replace it with the same structure. And we keep on doing this again and again and again. You would see a progression and how the curve becomes more and more complex. So you might ask which one of this is the actual Koch's curve. The thing is that none of them are the exact Koch's curve, because the actual Koch's curve has infinite amount of detail. And for practical purposes, it does not really make a difference, because beyond a certain point, our visual senses would not be able to differentiate between something that has detail infinitely long or has detail in the practical range to actually come very close to what we expect. So Koch's curve again is a mathematical object and it has exact self-similarity. So now if we observe, we can ask ourselves, what is the dimension of this Koch's curve? So remember, we started from a finite line and it had single dimension to start with. So if we think of the Koch's curve, now it has 4 copies that are exactly like the original Koch's curve. So we take one part of the Koch's curve and we multiply it by a factor of 3. And if we do that, as you can see on the slide now, it creates 4 copies. And so you can check yourself by doing the calculations that the fractional dimension comes out to be 1.26, which tells us that this is having dimension more than a line but less than a surface. It also opens up a very interesting point, that if you were to walk on this curve, what is the distance that you would be traveling? The answer is that there is infinite distance between the endpoints. And that is because you start with a finite length line, but you are increasing the length at every iteration. And if you do that to any number more than 1, so in this case you are increasing by a factor of 4 by 3, and if you keep on doing this ad infinitum, this would blow up, and so you have an infinite length. Furthermore, something more bizarre than that is that not only between the endpoints, but between any 2 points on the Koch's curve, you have infinite amount of length, which is very counterintuitive, but that is how mathematics has now been defined to now take into account infinites. And this has practical concerns when we think of questions like measuring the lengths of coastlines. In fact, one of the papers written by Mandelbrot that was published in Nature was dealing with the question of calculating the length of a coastline. So the exact title was, "How long is the coast of Britain?" So the western coast of Britain is quite jagged, and it depends on what scale of measurement are you using to calculate the coastline. If we use a very fine-grained scale of measurement, we are then going to catch many of the small indentations. But if we are using a very big scale of measurement, you're going to find a smaller coastline distance. And this has been the case. Whenever you see reports of coastlines, you would see that there is mass discrepancy. And this is because different measurement scale is going to give you different results. And this is one of the important messages when we talk of fractals. Typical statistics may not be very appropriate. In fact, in such a case, the actual length of the coastline would be infinite, like the length of the Koch curve was, because you have very fine details. If you keep on reducing your scale of measurement, the size of the coastline would increase and keep on increasing. So the way such a coastline should be measured is not in amounts of the distance, but in amounts of the fractional dimension. So this fractional dimension is also known as Hausdorff's dimension, and it has been calculated for Britain to be close to 1.25. So this means it is quite jagged. But if you were to consider an example of the coast of South Africa, which is quite smooth, you would see that it is very close to what you would expect for a line. This is 1.02. So using this, you can quantify the roughness of an object. Okay, so fractals do not always produce exact self-similarity. And the kind of self-similarity we are interested when we deal with data traffic is statistical self-similarity. So you would see on your screen now graphs from a landmark paper published between 93 and 95, in which it was shown that Ethernet traffic is self-similar. So let's observe this. There are 4 scales of measurement. In the first graph that you see on the top left, the interval is 10 seconds. So you see that it has some bursty characteristics. Let's aggregate the traffic and now see what is the case for 100 seconds. Similar properties. Again, you have burstiness. We observe that this is the case for 1000 seconds and 10,000 seconds. So over a range of 4 orders, you observe that the Ethernet traffic has self-similarity. But you would also observe that the self-similarity is not exact. They are similar, but not exactly the same. So we would call this statistical self-similarity. So if you have the mean and the variance and the autocorrelation coming to be about the same, you would say that they are statistically self-similar. You can think of them being drawn from the same distribution. Fractals have been used a lot in popular culture, and I'm just going to give you a glimpse of how they are being used. They are used for computer-generated fractals. So many times you would observe artificial sceneries in movies, and those artificial constructs look very natural because of being rugged and looking like natural objects. They are approximating the roughness of real objects. So they have been used for creating artificial pictures of planets and of mountains and of clouds. So you can read a lot about this if you visit Mandelbrot's site. He has sadly passed away in 2008, but he has an active site, Yale University's site, and from there you can find a wealth of information. Fractals have also been used in art. In fact, because of the beautiful nature of symmetrical patterns, we are often tuned or we are accustomed to finding beauty in patterns that are fractal-like. In fact, many artists have not been trained on such technologies. They did not know the terminology, but they were using many of the concepts of fractal that have now been formalized. So these are paintings by Japanese artist Hokusai, and you would observe that there is inherently fractal behavior shown in the paintings. Okay, so now we are going to move on to the topic of fractal statistics and how it's different from the traditional usual statistics that we would study in universities. Let's start by talking about non-fractal statistics. So when we talk of non-fractal statistics, the randomness that we are assuming is the mild randomness that we've talked in previous sessions. So if you observe, you would see on the screen now a schematic of how data varies around the typical value. You would see that most of the data is quite close to the typical value. And this may be called the bell-shaped world. We've talked earlier about how some processes are well approximated by such statistics, and we said that this mainly applies when the process that we are studying is constrained by certain physical, chemical, or biological constraints. However, if we talk of the financial world, if we talk of the network performance evaluation world, there are no such constraints. And then non-fractal statistics is wrong. So, but still, if let's finish the topic of non-fractal statistics. If we consider and assume that the original distribution is relatively homogeneous and is aptly captured by the bell-shaped distribution, the law of large numbers applies. So every time your distribution has finite variance, because of law of large numbers, if you keep on increasing the size of your sample, you're going to converge to the population mean. That is not the case when we talk of fractal objects, because in fractal object, there is huge diversity. So you have some very, very small objects, you have some small objects, you have some medium-sized objects, you have large objects, you have even gigantic objects. So if you have such wide diversity, you would see that now your distribution cannot be represented by the bell-shaped world. Now the distribution is more like a power law or a heavy-tailed distribution. This now corresponds to what we've been studying as the world of wild randomness. And in this world, the notion of mean and variance do not really apply, because we've studied earlier that for certain values of alpha for power laws, you will not have a well-defined mean. You will not have a variance value. Mathematically, these values are not defined. So if you keep on increasing the size of your observation, the sample mean is actually going to blow up to an infinite value. And this is where traditional statistics fail for fractal domains. So let's consider an example to illustrate this. We're going to see two games in which we highlight how fractal statistics are different from non-fractal statistics. The first game we're going to talk about is about tossing of a fair coin. So if we toss a fair coin, it is going to come up heads and tails with equal probability. So if you take the distribution, you can see that if you take a large enough sample, it is going to converge to the mean value. So if we were to play a game in which someone who gets a head is going to get $1, and if he gets a tails, he's going to get $0. If we were to play this game infinitely long, you would find that the expectation would be, for every game, the average expectation would be $0.5. Now let's change the rule of the game, and this was proposed by one of the Bernoullis and has come to be known as the St. Petersburg's paradox. And that is, the rule of the game now is, you toss a coin, if it comes head, you get $2. If it does not come as head, keep on doing this until you get a head, and then you're going to get 2 raised to n number of dollars, where n is the toss instance in which you got a heads. And now if we ask the question, what is the mathematical expectation of the value that you expect to win, then this comes out to be the average value is infinity. And that is because very far off values are mathematically possible. They may be having very, very minute probabilities, but they also have associated very large gains. And in the case of mathematical infinity, if you play some game very, very long, infinitely long, even the small probabilities are going to occur. And if you make the calculation, the average winning, the expected value comes to be infinity. This really conflicts with our intuition, because if we play this game, the average value that we would expect would be not more than 10. In fact, if you were to put an entry fee into this game, you would find really someone who would pay more than $10 to play this game. But still, the mathematical expectation is infinity. And this is because mathematics, the typical mathematics, the usual kind of statistics, does not capture the reality of fractal statistics. So we need to have some other methods. And the kind of methods we discussed when we were talking of power law are more appropriate here. So let's recap of that and tie those insights to this game. So if we create a graph in which the x-axis is the logarithm of the number of games, and the y-axis is the average amount you would win per game after n games, you would see that this average keeps on increasing. And in the limiting case, this would be infinity. Drawn in an alternative manner, in the manner we've discussed when we talked of power law distribution, if we graph the payoff versus the CCDF, we would see a power law decay. That is, we expect the distribution to go in a hyperbolic way, in a power law way. If you were to draw this on a log-log scale, you would have a linear line. So, message I would like to give is that for network traffic, the bell-shaped world does not really cut in. So we would have to actually use power law distribution most of the time. And we would have to revisit our assumptions. And in many cases, simple assumptions that we've made about traffic statistics does not work. So we'll continue this discussion in the next session, where we talk more about fractals and how self-similarity applies to network performance evaluation studies. Till next time, Assalamu alaikum.